we're going to do some problems using this equation. And some problems are harder than others, right? So the value of R we're going to use is 0.082058. And remember, for your final exam, you can bring a sheet of paper. I probably would put some of this on your sheet of paper. This is what I call Unit 5. There's no Unit 5 exam, but there will be Unit 5 questions on your final. So I'm going to jot down R is equal to, because I never can remember, 0.082. And liters, atmospheres per mole, Kelvin. So the units are very important. Again, are we all here? There are different values of R because they have different units. All right, so let's do a problem. So what I usually do is, I don't know why, it's kind of cheesy. I usually make a little box, and next to that box, I go ahead and write P is equal to V is equal to, come on, why is it not working?
What are you writing?
I'm trying to write, I know it's not, nothing.
Is your pen not on?
Let's see.
The one day she brings it from home and it doesn't work.
I know, right? It looks like it's on. Oh, no, I think the battery's gone. Because it's not working. Maybe it's not paired. Okay, we'll go back to the board. That works. Sorry, people who are listening to this, you can't see it. So, to streamline it, the problem, I do this. So I say what volume, so I put next to my volume, I put a question mark. Will 0.20 grams of carbon dioxide. So we know this is CO2 gas. Now, the grams actually, I'm going to tie it into number of moles. So I can take mass and use the molar mass to get to to get to moles. So I'm going to put my 0.20 grams here next to my N. Occupied pressure of 732 millimeters mercury. Now, do you see, actually, based on what we've been talking about, I have to fix this millimeters mercury. I have to get it in units of atmospheres. We talked about that 1 atmosphere is exactly equal to 760 millimeters mercury, so that's how I'm going to do that. And it gives me my temperature and DRAC. I got 22.0 degrees Celsius. I'm going to have to add 273.15 to get it to Kelvin. So I'm going to have to fix that. So bottom line is, if I have pressure, I can get to moles, I have temperature. What I don't have is volume. So I have to take PV equals nRT. If I want to get volume by itself, what do I do? What do you think? It's with pressure here, so how do I get it by itself? I'm going to divide both sides by P. Yep. And then I'm just going to plug and chug. So here's how my slides go. Okay. So I'm after volume, so what I do usually is I take the ideal gas law equation and rearrange it for what I'm trying to get. So volume is nRT over P. And then I go ahead and make sure my units all match up. I mentioned that the millimeters of mercury is going to have to go to units of atmospheres. The temperature Celsius is going to have to go to units of Kelvin. So you're going to need to be able to do that sort of thing. So I said we can use that mass and the molar mass of CO2 to get to moles. The molar mass of CO2 we did a lot when we did combustion analysis, so that's 44.01 grams per mole. Slow me down if you're trying to write it down. I'm not going too fast. So this sounds like something we did earlier in the class. So I'm going to start with that 0.20 grams over 1. And then I'm going to use the flip version of the molar mass because I want grams to cancel. So I'm going to take that times 1 mole over 44.01 grams. Seems like we did 10 billion of these this semester. That will give me units of moles, 2 sig figs. So you're looking at 0.0045 moles. Okay, cool. Now I still need to fix my pressure and my temperature. So remember, if you're given a Celsius temperature, you can add 273.15 units to get it to Kelvin. So since we're adding, we're going to round according to 1 decimal, and that leaves us at 295.2 Kelvin. So that's going to be our temperature. Now we need to fix our pressure. And we were given it in millimeters of mercury, and we recognize that 1 atmosphere, which is what we're trying to get to, is equal to 760 millimeters of mercury. So if we do it this way, millimeters of mercury cancel, we're left with units of atmospheres. I don't know if I probably mentioned it before, but this is an exact relationship, so no uncertainty brought, so we're allowed 3 sig figs. So you're looking at 0.963 atmospheres. So then we're ready to go back to our arranged ideal gas law equation and plug in your nRT and P. So when I grade these, because you will do some maybe for your final exam, I'm going to be looking for units. So you can't just plug in the numbers, you have to bring the units with the numbers. Okay, so in the top we need nRT. So N was 0.0045 moles. R is that 0.082058 liters atmospheres per mole Kelvin. Our temperature in Kelvin, we said, was 295.2 Kelvin. And then we need to pick up our pressure in atmospheres, which we said was 0.963 atmospheres. So now units of moles in the numerator will cancel. So moles will cancel with moles. Atmospheres, okay, moles cancel with moles. Kelvin will cancel with Kelvin. And we have units of atmosphere canceling. That just leaves us with units of liters, which is awesome. So how many sig figs? You think? Not 3. Yep, just 2. Yep, just 2. 2 sig figs, and what would the units be? You can either go by the V or what didn't cancel. Liters, yep, units will be liters. So I get 0.11 liters. That's it. Unfortunately, they aren't all that straightforward. I wish they were. That's more like an intro to Gen Chem problem. Let's do another one. Again, even before I start the problem, if I know it's a gas law problem, I have this going on in my mind. You know, P is equal to V is equal to N is equal to T is equal to. So this one says, what is the density of argon gas? We'll come back to that. Notice we have a temperature 25 degrees Celsius, and we have a pressure. Oh, good, we don't have to fix the pressure because it's already in atmospheres, 1.22 atmospheres. Now, it doesn't give us volume or number of moles, but my question mark here is grams per liter. So, do you see where actually that actually is, we can get to coming up with, if I come up with a number of moles per volume, that will be moles per liter. And then I can use the molar mass to get to grams per liter. That's exactly what we're going to do. All right, so here we go. So in this case, what I want to do is rearrange PV equals nRT to have N divided by V. Okay, so if I go ahead and do that magic, let me know if you have problems with the algebra. But solving for N over V, we get this relationship. N over V is equal to the pressure divided by R times T. So pressure, R, T in the denominator. Here we go, plug and chug. So our pressure was 1.22 atmospheres. We got to fix our temperature by adding 273 units. That brings you up to 298 Kelvin. All right, here we go. By the way, this actually is called the molar density. Instead of the regular density, grams per liter, it's moles per liter. So here we go. In the numerator, we have the pressure, 1.22 atmospheres. And in the denominator, we have R, 0.082058. Units of R are liters, atmospheres. In the denominator, mole Kelvin. And then the temperature was 298 Kelvin. So notice in this case, units of Kelvin clearly cancel. Units of atmosphere cancel. What didn't cancel was units of liters per mole in the denominator. If I want to take units or numbers out of the denominator, I can. I just have to flip it. So that's actually going to be units of moles per liter, which is exactly what we want. 3 sig figs, and you're looking at 0.0499 moles per liter. So now we need to use, and oh, I was trying to think what this was. This is argon, isn't it? So the gas is argon. Now we need to use the molar mass of argon to make the moles in the numerator converted to grams. So what's the molar mass of argon? Just gotta pick it off of here. It's that 39.95 grams per mole. So here we go. This is what we came up for the molar density. To get your regular density, grams per liter, we're going to use the molar mass from the periodic table for argon. 39.95 grams per mole. Units of moles cancel, and we have units of grams in the numerator and liters in the denominator. So rounding to 3 sig figs, we can come up with the density for that gas is 1.99 grams per liter. I'm glad I have my blipper back. All right. But wait, there's more. Okay, so I'm going to erase this stuff. Put my P, V, and T and kind of pull from the problem what I've got. All right. So I have a sample that is 1.07 grams of sample. Actually, I'm going to go ahead and put it next to my N. I'm going to say 1.007 grams. Okay. It exerts a pressure of 715 millimeters mercury. Now, in the back of my mind, when I see that, I'm going to have to convert that to atmospheres if I use my ideal gas law constant. And it gives me a volume of 452 milliliters. I'm going to have to convert that to liters if I'm going to use my ideal gas law constant. It also gives me the temperature, 23 degrees Celsius, which, darn it, I'm going to have to add 273 to get it to Kelvin. We can do that. So the question is, what is the molar mass? So, question mark, what is the molar mass? Units of molar mass are grams per mole. That's what molar mass are. So do you see where if I can use these 3 variables to knock out my moles, then all I got to do is I will put that moles down here and this grams right here. That's how we get to the molar mass of the gas that way. So let's find out the moles of this gas first off. Rearrange P equals nRT, getting N by itself, divide both sides by RT. So N is equal to PV over RT. It's a very easy to do the wrong algebra here. Plug in what we know for PV and T, and it looks like this. Oh, we need to fix some things, don't we? Our pressure was in millimeters of mercury instead of atmospheres. We know there's a relationship of 1 atmosphere is equal to 760 millimeters of mercury. So we use it this way, 1 atmosphere over 760 millimeters of mercury. Round to 3 sig figs because the 760 is exact. So our atmospheres are going to be 0.941 atmosphere. We need to fix our temperature by adding 273. Actually, we can add 273.15, but the 0.15 doesn't do us any good because we don't have any decimals with the 23. So round to 0 decimals, no decimals, you got 296 Kelvin. Now we're ready to plug and chug. Oh, no, one more thing, I forgot. Our volume wasn't even right. Are you serious? You guys have done a lot of this. To get from milliliters to liters, we're going to use the 1,000 milliliters in 1 liter. So we're going to multiply 1 liter of 1,000 milliliters. Give ourselves 3 sig figs, so that's 0.452 liters. Okay, now we're ready to substitute in. So the number of moles then is the pressure which was at 0.941 atmospheres times the volume, which is in liters, 0.452 liters. In the denominator, we have R, 0.082058 liters atmospheres per mole Kelvin. And also in the denominator, we have our Kelvin temperature, which was 296 Kelvin. So we're going to round to 3 sig figs. That will give us our number of moles. So I get 0.0175 moles. So that number here is going to go right here. So here in a minute, the next slide, all you're going to see is I'm going to take the grams, which is that 1.007 grams, divided by that 0.0175 moles. Okay, so that's a way to use a gas law problem to get to the molar mass of the gas. 3 sig figs, and you get a molar mass of 57.5 grams per mole. As long as the gas is behaving. But wait, there's more. There's always more. Maybe there's more. Yeah, there's more. That one. Ding. All right. There's all such different types of problems. Well, here's this other thing I want to talk about. So this is one of the things clear back when we did thermodynamic problems with calorimetry and all that. We came up with standard conditions, and I kept saying they're different for standard conditions for gases. So standard condition for gases is this: 0 degrees Celsius, which is, of course, on the Kelvin scale, 273.15, and 1 atmosphere. That's what we call standard temperature and pressure for gases. So the deal is if you take PV is equal to nRT, PV is equal to nRT, and you plug in a pressure of 1 atmosphere, you plug in a temperature of 273.15 Kelvin, and if you plug in 1 mole of your gas, your volume will occupy, the volume of that gas will occupy 22.414 liters. So that actually, you'll see that in chemistry problems. At standard temperature and pressure, 1 mole of gas will occupy that volume, 22.414 liters. Okay. So this is just to kind of show you, let's see, helium, atomic number 2, molar mass is about 4. So this is kind of showing you about 4 grams, about 1 mole. So we could say that if this is at 1 atmosphere and at 0 Kelvin, which is 273.15, no, sorry, yeah, 0 Celsius. 0 Celsius, which is 273.15 Kelvin, then this volume would be 22.414 liters. Molar mass of ammonia is about 15 grams per mole. Okay. In each of these cases, these gases would occupy that volume, 22.414 liters. Okay, so put that in the back of your mind. Now this is a cool one too. This is called the combined or general gas law, and we can rearrange PV equals nRT to get N and R by themselves on the right. The reason we would do that is R, of course, is a constant, and N just means, well, let's just put it this way. If we hold the number of moles of gas in our system constant, then it's going to vary, the pressure, volume, and temperature will vary, okay, according to this relationship. Okay, so if N is constant, of course R is constant, and then PV is equal to T. PV over T is constant. So where that helps us is this. That's not the whole thing. This is the whole enchilada, the combined gas law. We actually have 2 states. We have state 1 and state 2. State 1 and state 2. So state 1 is set up P1V1 over T1. State 2 is set up P2V2 over T2. Okay? So we have 6 variables there. And we can go ahead, if we are given 5 of those variables, we can find the 6th. That's the way that rolls. Okay. And there is kind of a cool catch to this. This right here, do you see R there? I don't see R in that equation at all. So if we don't use R, we are not a slave to these units. We're not a slave to liters. We're not a slave to atmospheres. We can have, volume can be milliliters, and another common pressure instead of atmospheres could be millimeters of mercury. We don't care because there's no R there. Okay, so actually let's look at this. We have a state 1 and a state 2. Actually, the next slide really does a good job of what I would usually do. You're going to see on the next slide where I put my state 1 here, my state 2 here. I knock out my P, V, and T for both state 1 and state 2. So if you read this a few times, you're going to see that actually it looks like this. State 1 pressure, 322 millimeters mercury. State 1 volume, 33.5 milliliters. State 1 temperature, 12 degrees Celsius. Now, a minute ago I said if you don't have an R, which we don't have to make sure our units of pressure or volume are anything other than to make sense. We do have to fix our temperatures. We cannot go with Celsius temperature. Okay, so from the original problem on the previous slide, we could come up with those state 2 conditions. The pressure of state 2 is 353 millimeters of mercury. State 2 volume, 46.7 milliliters. And state 2 temperature, that's what we're after. So again, we have, for this sort of problem, you have 6 variables. You know 5 of them, you're supposed to find the last one. It's really easy, easy to make an algebra mistake here. My favorite way of making sure I don't do an algebra mistake for this one is to, what I say, flatten it out. So probably on your, I don't know, maybe on the cheat sheet you're going to bring to your final exam, you might write this. No, I'm not good with trying to, and we're after this guy, right? Like, dang, it's like in the denominator. So what I usually do is, the way I flatten it out is I go across the equal sign and I multiply those. So P1, V1, T2 is equal to P2, V2, T1. That's just the way I learned it. Now if I put my little asterisk here, that's what I'm trying to solve for. It becomes pretty apparent that if I divide both sides by P1, V1, that'll work. Right? Because then these will cancel. I could rewrite this as T2 is equal to, and then this sometimes it's helpful to go ahead and grab my P2 over P1 times V2 over V1, and then see I'm kind of nesting those quantities, tagging along as T1. So you're going to see this here in a minute, and that's how I get there. That's how I get there personally. But I'm not a math teacher. Never have been, never will be. Okay, so we still got to fix that temperature though. Okay, so that temperature was 12 degrees Celsius. We know we need to add 273 units, so you're looking at 285 Kelvin as our T1. All right. So on the next slide, you're going to see that's the combined gas law equation, or general gas law equation. We're trying to get T2 by itself, and it ends up taking on this format, just like I said. Now, it's just, we have 2 P's and 2 V's and 2 T's, and we have these subscripts 1 and 2, so you're just going to have to be careful. So the temperature for the second state is a ratio of P2 to P1 times V2 to V1 times T1. So now we're ready to plug in. So now can you kind of see where the units don't matter for pressure and volume? Because the units of millimeters of mercury are going to cancel out. But you have to stay organized, and it's P2 over P1. So that's a 353 millimeters of mercury over 322 millimeters of mercury. The V2 over V1 looks like this. 46.7 milliliters divided by 33.5 milliliters. Of course, units of milliliters cancel out. It's wonderful. And then our T1 in units of Kelvin was 285 Kelvin. Again, don't let it throw you off. Don't be thrown off by leaving it in Celsius. So around to 3 sig figs, you're looking at a T2 Kelvin temperature of 436 Kelvin. So I'd have to go back to the original problem, but I think it said what would the state 2 temperature be in units of Celsius. So instead of adding 273, we have to subtract 273. So if we take that Kelvin temperature of 436 Kelvin, and from it subtract 273 units, you get 162 Celsius. That's it. QED. Okay. So to kind of follow up on that, we have these kind of versions of it. So let's kind of make this. And you don't have to memorize these other versions. If you know P1, V1 over T1 is equal to P2, V2 over T2, that will get you down the road. So what this says is, what if your temperatures are held constant in addition to your number of moles? Well, then it just simply becomes, what's in the numerator? P1, V1 is equal to P2, V2. And we could kind of look, what if your volume is held constant? Well, then it simply becomes P1 over T1 is equal to P2 over V2, or excuse me, P2 over T2. And then finally, if your pressure is held constant, then you end up with this version. V1 over T1 is equal to V2 over T2. So they're just different versions of the combined gas law equation. All right. So on to part 3. So remember how this works. You don't have to do ALTA, but it's worth extra credit. 100 points for every ALTA part that you do. But then also remember that you can do OpenStax homework and get 50 points extra credit. Okay?
When do we have to have that in by?
Good question. I think next Friday when you come take the final.
Okay.
Yep, that should all work.
And can we send you a picture of the OpenStax homework we've been working on?
Yes. Yes, you can. Okay. But wait, there's more. Nope. Okay. So, this is a little bit different. We're going to have to kind of get the cobwebs off of what we know about working stoichiometric calculations. I wish my pen worked. That just is terrible. I don't know. I wonder if you click it. It's just mad. Okay. So, I think I'll just, all right. I'm going to rewrite this. Zinc, 1 mole of zinc, solid, plus 2 moles of HCl, aqueous, goes to form 1 mole of zinc chloride, aqueous, plus 1 mole of H2 gas. All right. So what are we given? It says, what is the volume of H2 gas? So I'm going to say V is equal to question mark. Notice that it gives me the temperature of the gas. T is equal to 22 degrees Celsius. Now I may not need to use it, but I'm going to jot it down. The pressure of the gas is 1.00 atmospheres. Can be produced by using 2.50 grams of zinc and excess HCl. So, that's when we did stoichiometric calculations, I'd say, what do you know most about? Well, actually, do you see where we can take this mass and we can go to moles of zinc, and then we can use a stoichiometry between the zinc and the hydrogen gas, which is a 1-to-1, to go to moles of H2. And then once we have the moles of H2, we can use PV is equal to nRT, solve for V. That's exactly what we're going to do. Okay, so we need to know the moles of zinc. We can use the periodic table, knock out its molar mass. From the periodic table, you find it's 65.39 grams per mole. So to get to moles, we take the 2.50 grams of zinc times 1 mole over 65.39 grams. 3 sig figs, then that leaves us with 0.0382 moles of zinc. 0.0382 moles of zinc, yep. Use the stoichiometry to get from moles of zinc to moles of H2 using the stoichiometric ratio. Okay, so we're going to start, our starting term is going to be the 0.0382 moles of zinc over 1. And I hope you guys buy this. The stoichiometry between them is a 1-to-1, so I'm going to put 1 mole of H2 over 1 mole of zinc. Moles of zinc cancel. Of course, I could do that one in my head. That means we also have 0.0382 moles of H2. Okay, so we're getting close. Now, what we've been doing before is I need to turn my attention to BV equals nRT now and solve for V. I divide both sides by P, and it looks like this. So V is equal to nRT over P. Oh, and then we need to make sure we fix this 22 degrees Celsius to Kelvin by adding 273. 22 degrees Celsius plus 273 newtons gets you 295 Kelvin. And I think that's it. So now we can plug and chug, I think. So volume in the numerator, we have the number of moles, which we said was that 0.0382 moles. Also in the numerator, we have the R, 0.082058. Units of R are liters, atmospheres per mole Kelvin. And then also in the numerator, we have the Kelvin temperature, 295 Kelvin. In the denominator, we simply have the pressure, which was 1.00 atmospheres. So unit-wise, our moles have canceled. I love canceling units. Moles have canceled, Kelvin is canceled, and units of atmospheres have canceled. We're left with units of liters in the numerator, of the numerator. So that's awesome. 3 sig figs, that puts you at 0.925 liters. So that would be the volume of H2 gas that we produced at that temperature and that pressure. I mean, these have very practical applications in real life. Okay. All right. But wait, there's more. There's always more. Okay, we can do this one. That's probably the last one. All right, so I'm going to go ahead and, since I can't write underneath it, rewrite the balanced equation and kind of see what we got. So N2 gas combines with H2, 3 moles of H2 gas to form 2 moles of NH3, also gas. So under the H2 gas, I'm going to put V is equal to 125 liters. And I'm going to go ahead and put T is 298 Kelvin, 25 Celsius. And I'm going to go ahead and say P is equal to that 0.783 atmospheres. Wow, we don't have to convert anything there. How fun is that? Notice it says nitrogen is in excess, and we know what that means. That means that in order to find out how my reaction is going to unfold quantitatively, I only have to worry about this reactant because it's in limited supply. How many liters of ammonia, so volume, question mark, under ammonia, can be measured at STP, can be produced. So what's the temperature at STP is that 273.15 Kelvin. The pressure at STP is 1.00 atmospheres. Okay. All right. Well, do you see where I can use these three things to get to my n? And once I know n, I can use stoichiometry to get to that n. And once I have that n, I can go ahead and get to my v. So actually, we are bumping up against the clock. So hold that thought. Go ahead and finish that thought. But I'm going to finish this problem on Monday. We'll take off from there. Take off. And there's still stuff left up here. So, take for the road.
Is our final gonna be multiple choice?
Where were you? It's on the little sheet I gave you. It's half and half.